Welcome to my presentation. My name is Jefferson Núñez Povis. The topic of my presentation today is what is soft robotics and how we can carry it out. Let me ask you a question. Have you ever wondered how robots in the future will look like? The reason that this topic is interesting for you is, for instance, for industries, it will become a great update in terms of performance and efficiency, and in general for humanity, who's interested in achieving robots that can perform as well as humans or even better. We are going to talk about three things. Firstly, why it is necessary to carry out soft robots. Secondly, materials and technologies available to design soft robots. Finally, we are going to talk about optimization of control for soft robots. First of all, why it is necessary to carry out soft robots. By soft robotics, we mean robots that can move in a safe, smooth and efficient way. One of the reasons that motivated research for soft robotics was the lack of an actuator that can compete in motion with natural systems like musculoskeletal system. Another reason concerned the safety of operations in which humans were involved, because it was expected that working with robots doesn't mean higher risk than working with humans. Approaches made were retrofitting the design by increasing sensorization, designing robots with the idea of safety in mind, like DLR's lightweight robot, and soft robotics, introducing mechanical compliance and damping in the design. It's also important to look at the resilience of the robot in an unpredictable environment, which can result in damaging a human or the robot itself during its performance. It's also important that the high performance and energy efficiency a soft robot can reach due to the adaptable compliance to store energy better than rigid robots and the velocity they can perform a task. They represent a new way of control system that until then was divided in position-based controllers and torque-based controllers regarding the joints. As position-based were more used and simpler, and torque-based offered more versatility, the introduction of soft robotics gave the possibility of setting natural equilibrium position of the joint and stiffness by which the joint was attracted toward it when loads were applied. Next, we move onto materials and technologies available to design soft robots. It's important to mention natural muscles because they are the inspiration to achieve soft robots, due to its mechanical properties that differ from conventional actuators, like stiffness and capability to store, release and dissipate energy. A simpler comprehension of soft actuators comes from breaking it down into two parts: energy storage elements that keep energy, and transducers that allow the flow of energy, which can be dissipated, turning them into energy sinks, or injected inside the system, turning them into energy sources. The technologies used as sources for soft actuators can be pneumatic and hydraulic, which can be low and high impedance respectively. Impedance is the relation between the force applied and the displacement occurred in a point. Electromagnetic and electrostatic actuators being the last ones, more suitable for micro and nanoscale robotics. Also for nanoscale applications is useful the reverse piezoelectric effect, which is the production of a stress and or strain when an electric field is applied, and the electro and magnetostrictive effect of some materials, which is the tendency to change their shape under a magnetic or electric field to produce microscale actuators. Shape memory alloys, copper, zinc, aluminium, or polymers are convenient materials for soft actuators, while being polymers more versatile because they can be biodegradable and change from elastic to rigid, but they have major inconvenience like energy inefficiency. Carbon nanotubes have an even greater potential in the development of artificial muscles. It's been proved that the best way to store energy is in the way of elastic energy, but also it is possible to store it in kinetic form using systems similar to Formula One racing cars. It's important to look at the energy sinks, which can be dissipation systems and dampers, without which the robot can perform potentially dangerous. Dampers can be obtained with different principles like friction, heavy currents, and fluids with the backdrops of high hysteresis, low damping torque at high velocity, and residual oscillation in respectively. There are several combinations of these elements to achieve soft actuators, with examples like series elastic actuators and variable stiffness actuators. Finally, we are focusing on the optimizing control for soft robots. One important tool to determine the best relation between design and control of our soft robot system is the optimal control theory. It provides a reference from which we can compare different systems, and it's an element key in understanding planning and control methodologies for soft actuators. Examples in which it can be applied are the safe rachistochrome problem in variable stiffness robots, which consists in choosing the best trajectory in performing a task in the shortest time, and in the case of a sudden impact, it limits the impact force, or it could be the opposite, which is maximizing the velocity of an elastic robot to maximize the impact itself. In conclusion, in this presentation, my objective was to give a general impression of the current situation of soft robots.